Good day, viewers. We are welcome back to another interesting physics class where we are going to be reviewing the topic density. Um, Density is a very popular topic in physics, and I hope we are going to have an interesting time discussing about it. Uh, Density is quite simply the mass per unit volume of a substance. The density of a substance is the mass per unit volume of that substance. It is usually represented with the Greek letter rho, and we said it is the mass of the substance all over the volume of that substance. That is the definition of density, the mass per unit volume of the substance. Density helps us to understand how compact a substance is. There are some substances that could look so big, but they're actually very light. Yes, being big means they have a large volume, but being light means their masses are actually very small. So when you find their density, you get the density, you will see that the density of those type of substances are actually very small. It is the density that helps us to understand how heavy an object will feel, even though you have a small or large volume of it. There are so many substances that are very small in size, but you cannot carry them. Yes, their volume is small, but their mass is large. So by the time you calculate their density, it is actually very big. A very good example that I want to draw here is the illustration of two liquids, and mercury. Almost everybody here can carry a 5 liter keg of water, but there's actually nobody, a student, or let me say, you will find it very difficult to carry that same 5 liter keg of mercury. Yes, 5 liters, both of them have the same volume, but 5 liters of water actually weigh less, far less than 5 liters of mercury. 5 liters of mercury is heavier. So when we take into account the mass and the volume of a substance to understand how heavy it is, what we are trying to do is density. So density of a substance is just the mass of the substance divided by the volume of the substance. It is a scalar quantity, and the two quantities that we are going to use to calculate it are also scalar. Density does not have direction, mass does not have direction, volume does not have direction. The unit of density is, the unit of mass is kilogram, while the unit of volume is meter cube. So therefore, we expect that the unit of density will be kilogram per meter cube. Per represents the fact that you are dividing the quantities in these units. So density can also be expressed sometimes in grams per cm cube, If the mass is put in grams and the volume is put in cm cube, then the unit will be grams per cm cube. Oftentimes, we are required to convert from one unit to another. It is not a problem for us to convert. I would like to convert a particular density value in kg per meter cube to grams per cm cube so that we start to see how the conversion can be easily done. For example, and that is what it is, the density of water is 1,000 kilogram per meter cube. The density of water is 1,000 kilogram per meter cube. If I want to change it to grams per cm cube, I would like to use the conversion of units by multiplication. And this can also be applied to all other units. You can use it to convert from kilometers per hour to meters per second. You can use it to convert from meters per second back to kilometers per hour. Please let us look at how that can be done. The density of water is 1,000 kilogram per meter cube. I can write kilogram per meter cube like this. I can also write it like this. They actually mean the same thing. So what I will do is I will get the conversion of kilogram to gram. I want to convert from kilogram per meter cube to grams per cm cube. I'll get the conversion of kilogram to gram, and I'll get the conversion of meter cube to centimeter cube. From kilogram to gram, we all know that 1,000 grams makes 1 kilogram. We learned that long ago. 1,000 grams makes 1 kilogram. I will put that into a fraction and I will use it to multiply what I already have. 1,000 grams makes 1 kilogram. That is it. I just put 1,000, did that conversion into fraction form. But why did I not put kilogram up? Because I was looking at the possibility of kilogram cancelling out with kilogram. That can only be achieved if I make this kilogram my denominator. So I want to convert meter cube to centimeter cube. Yes, because it has a cube, that can be a little bit challenging, but one very easy way to do it is try to know how to change meters to centimeters. If I know how to change meters to centimeters, all I just need to do is I will cube this quantity and I will still be able to get the conversion that I need. How do we change from from meters to centimeters? The conversion from meters to centimeters is 1 meters is 100 centimeters. 1 meters is 100 centimeters. If I write that one down, then I can cube this conversion. I can cube every item in this conversion. If I do that, I will have 1 cube, 1. Meter cube is still meter cube. 100 cube is 1 million. Centimeter cube is centimeter cube. So I can say that clearly 1 meter cube is 1 million centimeter cube. I can also put that in a fraction and use it to multiply what I already have. So I'm going to write it as 1 meter cube makes 1 million centimeter cube. If that is the case, then I can just cancel out what I already have. I'll cancel out meter cube by meter cube. And that is the reason why I had to put the meter cube up. I wanted to cancel what I already have. That way, 3 zeros can cancel out these 3 zeros, and 3 zeros can cancel out these 3 zeros. So quite simply have the density of water to be 1 grams per cm cube. 1 grams per cm cube. I know several people that will tell you that anytime you are converting from a unit of kg per meter cube, anytime you are converting from kilogram per meter cube, and you are converting to grams per cm cube, all you just need to do is you divide by 1,000. That is correct. So if I divide by 1,000 in kg per meter cube, I'll get density in grams per centimeter cube. But this is where that 1,000 came from. If you have it in grams per cm cube too, and you want to convert to kg per meter cube, all you just need to do is to multiply by 1,000 and you get the right answer in that unit. So to determine density, all you need to do is just divide the mass of the substance by the volume of the substance and you get the density of that same substance. That is very easy to do. We move on now to how to find the density of a mixture. I just told you there are densities of different substances that are available in textbooks and even online. If you need the density of any substance, all you just need to do is check your textbook or check online, you definitely have them. Water, for example, has a density of 1,000 kg per meter cube. Mercury has a density of 13,600 kg per meter cube, and so on and so forth. What does density of 1,000 kg per meter cube for water? What does it mean? Density is 1,000 kg per meter cube. Quite simply, if I need to explain this, anytime we use per in physics, it means in one or for one. What I am trying to tell you is that if you have 1 meter cube of water, if you have 1 meter cube of water, its mass, it will have a mass of 1,000 kg. Anytime you have 1 meter cube of water and you weigh the mass, you find the mass, you discover that the mass is 1,000 kg. So from there, I can now decide to get the masses of every other volume quantities, volume values that is given. If I have 2 meter cube of water, it means I will have a mass of 2,000 kg of water. 3 meter cube of water will have a mass of 3,000 kg. 4 meter cube of water will have a mass of 4,000 kg. 5 meter cube of water will have a mass of 5,000 kilograms. And that is all that is there to know about density. Now we move on to density of a mixture. When you mix two different substances together, what will be their density? If, for example, I decide to mix water and mercury together, will the density be equal to density of water 1,000? Will it be equal to the density of mercury 13,600? Or will it just be equal to the median, the mean of the two densities? That is not the case. We do not add densities together and we don't subtract density together from each other. What we do is we are going to try to treat the mixture as if it is an entirely different substance from water and mercury. We don't add density. Any quantity in physics that is obtained by dividing two other quantities cannot be added. I cannot find total speed because speed is distance over time. So I cannot find total speed. If I need to know the speed, if I need to know the average speed after you have been through series of speed values, what I have to do is I'll go back to how I calculated the speed initially. I'll go and get the total distances. I will divide it by the total time values that has been given. So anytime we have two different substances mixed together, we do not add their density. So the density of water and mercury will not be 14,600. We have to find the total masses of water and mercury that I have added, and I will divide it by the total volume of the water and mercury that I have added. And I will now get the average density or the mean density of what I now have. What I just know is anytime you mix two different substances, what you will have, the density that you are going to have, anytime you mix two or more substances, the density value that you are going to have for the mixture will not be up to that of the substance with the maximum density, but it will be more than the density, the least density in the mixture. It will not be up to that of the greatest density in the mixture, but it will be more than that of the lightest substance in the mixture. So if I have to find the density of a mixture, I must get the mass of the mixture and I must divide it by the volume of the mixture. That is when I will get the density of the mixture. Now to do that, I have to take a cut a little to see other things that can be given instead of density. Instead of density, I can be given what is called a relative density. Substances also have relative density values that can be obtained from their density values. The relative density of a substance is usually taken to be the density of that substance divided by the density of water. Why are we dividing by water? Because we understand water. We understand how heavy water is. If I put water inside a cup, you don't even need to know how, you don't need to be told how heavy it will be. If you are going to carry a cup filled with water, you know, you have an expectation of what the weight will be. Water is a substance that we know very well. We know its weight, we know it does not have color, it does not have odor. So when we now describe certain substances to you and we describe them relative to water, it gives you an idea of how heavy that substance will be. For example, if I tell you that the substance is twice as heavy as water, you understand how it can be because you understand water very well. If I tell you that the substance is 1,000 times heavier than water, then you start to have an idea that if you are carrying a cup of that substance, it's like carrying 1,000 different cups of water. So water is what we compare, the density of water is what we compare the density of the substance by before we know the relative density of the substance. For example, if the density of mercury is 13,600 and the density of water is 1,000, I can find the relative density of mercury by doing the density of mercury divided by the density of water. The relative density of a substance is the density of that substance divided by density of water. So that clearly will be 13,600 divided by 1,000, which is the density of water. And if I divide, I'm going to have 13.6, sorry. So the relative density of mercury is 13.6. What that means is that substance, mercury, is 13.6 times heavier than water. If you are carrying a gallon of it, it is like carrying a 13.6 gallons of water. If another substance let's assume that a substance has a density of, a substance K has a density of 780 kg per meter cube. And I want to find the relative density of that substance K. It will be the density of the substance divided by the density of water. What would that be? 780 divided by the density of water. What's the density of water? 1,000. If we divide it, we should have 0.78. Relative density does not have units because we are dividing two different quantities that have the same units. So 0.78 is the relative density of that substance K. It means that that substance is not as heavy as water. If the relative density of a substance is less than 1, it's not as heavy as water. If it is 1, it means that substance is as heavy as water. If it is greater than 1, it means that substance is heavier than water. So if the relative density of this substance is, the relative density of substance I just got is 0.78, it means that substance is lighter than water. Now, there are so many things that we do with relative density. There are so many times that we will need density and we'll give you relative density values. If you have relative density values, I expect you to be able to convert that to density. For example, if within this expression, I know the relative density and I know the density of water, I can find the density of that substance. If I make it the subject of the formula by cross multiplication, I will see that the density of a substance is the relative density of that substance multiplied by the density of water. So when you give me the relative density of a particular substance, I only need the density of water before I can now get the relative density. Let us try an example. If I'm giving the relative density of a substance P or Z to be 5, I can easily find the density of that substance. The relative density of Z must be equal to the density of Z all over the density of water. So to find the density of Z, I will just cross multiply. That means the density of Z is equal to the relative density of Z multiplied by the density of water. And that will be, the relative density of Z will be 5 multiplied by the density of water, 1000 kg per meter cube. That is why it is very necessary for a physics student to know the density of water in solving any question, though usually those are always given as a constant in any density question that require you to use them. Now, so what I've said briefly is we have been able to look at the formula for density, we have been able to look at the relative density of a substance, how to get relative density and how to get density from relative density. So the next time you need density and they give you relative density, just remember that all you need to do is to just multiply it with the density of water and you get the density of that substance. Now we'll go back to the density of a mixture. How do we get the density of a mixture? If I have mixed up substances A and B together, if I mix substances A and B together, the density of that mixture must be the mass of the mixture, the total mass of the mixture, or the mass of the mixture. That's the total mass of the constituent of the mixture divided by the volume of the mixture. There are instances where you mix substances together and there will be a contraction or an expansion on mixing. Some substances will mix together to react, thereby reducing their volume. Some substances will expand probably upon reaction also anytime you mix them. But we are going to solve this for situations where there are no change in the volume of the substance when you mix them. If I had a substance A whose volume is 3 meter cube and a substance B whose volume is 2 meter cube, if I add them together, it should give me a mixture whose volume will be 5 meter cube. But we are going to see that. So if I mix substance A and B together, the density of that mixture must be the total masses of A and B, mass of A plus mass of B divided by the total volume of A and B. That is volume of A plus volume of B, provided there's no contraction or expansion upon mixture. And that should give me the volume. We're going to take one example or two examples just to further understand what we are how we can determine the density of a mixture or how we can find an item from the density of a mixture. And we have some questions here that we can go through. An alloy of gold and quartz has a mass of 150 grams. An alloy of gold and quartz has a mass of 150 grams. Determine the mass of gold in the alloy. Relative density of gold is given to be 19.3. The relative density of quartz is given to be 2.6, and the relative density of the alloy is given to be 6.5. We are told to assume that there is no change in volume when the metals form the alloy. We should understand that alloy is a mixture of two or more metals. Here we are told that gold and quartz are mixed together. Gold and quartz are mixed together to get the alloy. I prefer to put this in a table form. Each of them will have its mass, volume, and the density. Each of them will have its mass, its volume, and density. I will have mass of gold, volume of gold, density of gold. The same thing for quartz and the alloy. The alloy represents the mixture of gold and quartz. So we have been given the relative density value for each. We have been given the relative density. I know the relative density of gold to be 19.3. The relative density of gold is 19.3. I also know the relative density of quartz to be 2.6. That is a lot lighter. And the relative density of the mixture, which is the alloy, is 6.5. That's what I told you. When you mix two different substances together, you are so sure that the density of what you are going to get will lie between that of the heavier and the lighter substance of the two. Now, we are also told that the alloy has a mass of 150 grams. We are told that the alloy has a mass of 150 grams. The mass of the alloy is 150 grams. The mass of the alloy is 150 grams. We are now asked to find the mass of gold that is present in the alloy. What is the mass of gold that is present in the alloy? M. The mass of gold that is present in the alloy, I will represent it with letter M. So, and I will try to complete or fill this table with just all the other terms. Those ones that I cannot find, I will try to see if I can express them in terms of M, and that should just be it. Now, if the mass of gold is M and the mass of the alloy is 150, and the mass of the alloy has to be the mass of gold plus the mass of quartz, it means I can express the mass of quartz in terms of 150 and M. This plus this must give us this. So quite simply, I can say that the mass of quartz will be 150 minus M. 150 minus M. So you see that when you add M to 150 minus M, you will get 150. That is it. Now, I told you again that we can get density values from relative density values. We can get density values from relative density values. The relative density of a substance is the density of that substance divided by the density of water. That means the density of a substance, if I cross multiply, will be the relative density of the substance multiplied by the density of water. So now, for gold, if the relative density is 19.3, it means the density of gold will be the relative density of gold multiplied by the density of water. And the relative density of gold is 19.3. For the density of water, I will use 1 grams per cm cube. I told you at the start of this class that the density of water can either be 1000 kg per meter cube or 1 grams per cm cube. But why have I chosen to use 1 grams per cm cube? Because the predominant unit in this question is grams. 150 grams, 150, which is the grams, which is the mass of the alloy, is expressed in grams. So it is good that I put every other unit in the unit that is consistent with what has been given to me. So I'm going to write this as grams per cm cube. So clearly, the density of gold will be 19.3 grams per cm cube. So the density of gold is 19.3 grams per cm cube. The density of quartz will be similarly 2.6 grams per cm cube. And I can also obtain the density of the alloy as 6.5 grams per cm cube. 6.5 grams per cm cube. So if I know those three, I can now express their volume. I can express their volume in terms of what I have. If density is mass all over volume, it means that the volume, if I make it the subject of the formula, must be equal to mass all over density. Mass all over density. And if that is the case, I can find the volume here by doing the mass all over density. I don't know the mass. I don't know the mass, but I know that the mass here is represented as M, and the density is represented as 19.3. Here too, the mass is represented as 150 minus M, and the density is 2.6. For the alloy, the mass is 150, and the density is 6.5. If I divide 150 by 6.5, I should have 150 divided by 6.5 should give me 23.07, 23.076 or 23.077 in cm cube. So that is it. So it clearly means that I have been able to populate this table with the quantities that have been given, and the one that have not been given, that is the item that I need, is the mass of the gold. I've expressed whatever I cannot find, I've been able to express it in terms of M. So now I can now get what I need by simply just doing, I know that there's no change in volume upon mixing. If there's no change in volume upon mixing, it simply means that the mass, the volume of gold plus the volume of quartz must give me the volume of the alloy. The volume of gold plus the volume of quartz must give me the volume of the alloy. I believe that if I solve that expression, I'll be able to get M that the question required that I should find. So I'm going to do M all over 19.3 plus 150 minus M all over 2.6 must give me 23.077. So I can find the LCM here, or I will multiply the two since they are decimal numbers. 19.3 multiplied by 2.6 should give me 50.18. 50.18 divided by 19.3 is 2.6. 2.6 times M is 2.6 M plus 50.18 divided by 2.6 is 19.3. I'll use 19.3 to multiply 150 minus M. So if I do that, it must be equal to 23.077. And if I try to open the bracket, I will have 26M, 2.6M plus 19.3 times 150. 19.3 times 150 should give me 2895 minus 19.3M divided by, must be equal to, if I use this to multiply it, I will have 50.18 multiplied by 23.077, and that should be 1158.00. If I collect like terms, I should have 2.6M minus 19.3M is equal to 1158 minus 2895. That should give us 2.6 minus 19.3 should be 16.7M must be equal to 1158 minus 2895. The answer is minus 1737. So you cut out the minus and you can find the M. The M must be equal to 1737 divided by 16.7. And the mass should be equal to, divided by 16.7, and the mass should be equal to 104.01 grams. And that is the mass of the gold that we're expecting. So we'll take another question to completely drive home our point so that we can understand how to determine whatever we need through the method of mixture, the method of the determination of the density of the mixture. Generally, anytime I have the mixture, I always represent them on the table. With the table, I will be able to find whatever it is that I need to find. So another question that we are going to take now is this. A 1000 cm cube vessel is filled with two liquids, L1 and L2 of relative densities. L1 has a relative density of 0.75 and L2 has a relative density of 1.85. If the relative density of the mixture was found to be 1.5, what volume of each liquid enters the mixture? Assuming again that there is no volume change when the liquid were mixed together. So here too, I have liquid L1 and I also have liquid L2. Then I have their mixture. I should be able to know the mass of each, the volume of each, the density of each. The density can come from the relative density, and with those information, I should be able to get whatever it is that they want me to find. They said with 1,000 cm cube container or vessel was filled with two liquids. That means after adding the two liquids, their volume got to 1,000 cm cube, became 1,000 cm cube. So that 1,000 cm cube will represent the volume of the mixture. Liquid L1, liquid L2 were put inside the vessel, and the volume of the vessel is 1,000 cm cube, and the two liquids completely fill that vessel. That means their total volume will be 1,000 cm cube. We are told also that the relative density for L1 is 0.75, for L1 0.75, for L2 the relative density is 1.85, for L2 the relative density is 1.85, while for the mixture the relative density of the mixture is found to be 1.5. So with the relative density we can find the densities. The relative density, don't forget, the relative density of a substance is the density of the substance over density of water. That means that the density of a substance will be the relative density of that substance multiplied by the density of water. What is the relative density of L1? Is 0.75. What's the density of water? I'm still going to use 1 grams per cm cube since the predominant unit in this question is cm cube. So the density of the substance clearly will be 0.75 grams per cm cube. If you are getting grams per cm cube, if you are getting your density in grams per cm cube, it will have the same value that it has, that is relative density has. So this will be 0.75 grams per cm cube. That's the density of liquid L1. 1.85 is the density of liquid L2, and the liquid L3 will have a density of 1.5 grams per cm cube. I want to find, this question has asked me to find the volume of each of these constituents that goes into the mixture. Yes, we know that their total volume is 1,000. The volume of L1 and L2 that goes into the mixture must be, let me assume that the volume of liquid L1 is V. If the volume of liquid L1 is V, then the volume of liquid L2 must be 1,000 minus V, because as we understand, when you add L1 and L2 together, it should give you a total volume of 1,000. If that is the case, I can now continue to solve my problem with V. So once you assume a letter, I will advise that you don't assume any other letter. One way by which some students will have done this is to call the volume of L1 X and the volume of L2 Y. In that case, you now have two different letters, and you must be able to get two independent equations that you are going to use to solve the problem. Now, but with this, I can continue. So now that I have assumed a value for my volume, I can get their masses in that quantity. Remember that the density is mass all over volume. Density of any substance is mass over volume. That means the mass of a substance will be density multiplied by volume. So to get the mass of L1, I'll just multiply its density 0.75 by its volume. That should be 0.75 V. To get the mass of L2, I'll just multiply its density by L, the volume. That will be 1.85 times 1,000 minus V. To get the mass of the mixture, I will just multiply its density by its volume. That should be 1.5 times 1,000. That should be 1,500. with what I've been able to find now, I can now write an equation for the masses that I have just obtained. The equation, it means the mass of L1 plus the mass of L2. If I add them together, it must give me 1,500. If that is the case, I will have 0.75 V plus 1.85 multiplied by 1,000 minus V is equal to 1,500. If that is the case, I can break this bracket. I will have 0.75 V plus, if I multiply, I will have 1,850 minus 1.85 V is equal to 1,500. So if I subtract, I think I will have minus, if I collect like terms, I will have 0.75 V minus 1.85 V is equal to 1,500 minus 1,850. If I do that, I will have minus 1.1 V is equal to minus 350. Clearly, V must become minus 350 divided by minus 1.1, and V must be equal to 350 divided by 1.1 should give us 350 divided by 1.1 should give us 318.18. 318.18 centimeter cube. That is the volume of L1 in the mixture. The volume of L2 in the mixture must be 1,000 minus V. That's 1,000 minus 318.18, and that should be 681.82 centimeter cube. And with that, we have come to the end of this problem. Now, we'll move on to Archimedes' principle. Archimedes' principle is one of the laws that we have to learn under density, and it simply states that when an object is wholly or partially immersed in a fluid, and an object is wholly or partially immersed in a fluid, it experiences an upthrust, which is equal to the weight of the fluid displaced by the object. I'll go over that again. When an object is wholly or partially immersed in a fluid, it experiences an upthrust, which is the weight of the fluid displaced by the object. It is common knowledge that if you have ever used a well before, if you have ever had to draw out water from a well, while your bucket is still inside the water, you can actually bring this up even with only one hand. You can bring it up with only one hand. But the moment it crosses the level of water inside the well, that is when you start to understand how heavy the object is, really. Now, that is just because anytime an object is inside a fluid is a general word for both gases and liquid. Anytime an object is inside a fluid, there is a particular force that the fluid is exerting on that object, that the fluid is using to push out the object from within it. The name of that force is called the upthrust. Anytime an object is inside the fluid, either it is completely inside the fluid or it is just partially inside the fluid. That means a part of it is inside the fluid. Anytime it is like this or like this inside the fluid will exert an upward force, trying to use it to push out the liquid, to push out the object from within it. The name of that force is called upthrust. And one significant achievement of this Archimedes principle is that it was able to tell us how we are going to determine that upthrust. The law explained how we are going to determine the upthrust by saying that the upthrust is the weight of the fluid that object has displaced. Now, how do I do that? How do I explain that? We all know that if you have liquid inside a container and you immerse an object inside the container, we expect that the level of the liquid inside the container will rise. now the level of the liquid inside the container must rise. Usually, this can be seen in the method of determination of the volume of an irregular object. If, for example, I have a measuring cylinder that is graduated to know the level of water inside it, and I pour water inside it up to, let's say, this point is the 20 centimeter mark, 20 centimeter cube mark. It means the volume of water inside this container is 20 centimeter cube. If I now immerse an object, and after that, the level of the liquid rose to 25 centimeter cube, it simply means that the volume of this object that I have immersed is equal to 5. That is the difference between the two levels that I had before and the one that I have now. So this can be used to determine the volume of an irregular object. There are some irregular objects that we cannot determine their volume. In fact, we cannot determine irregular objects, the volume of irregular objects, by calculation using any mathematical formula. If it is regular, it will have a mathematical shape that we can ascribe to it, and we can find its volume. If it is a sphere, it is 4 pi r cube, 4 over 3 pi r cube, sorry. If it is a cylinder, it is pi r squared h. If it is a cone, 1 over 3 pi r squared h. If it is a cube, it is L cube. If it is a cuboid, then it is length times breadth times height. But if it is an irregular object like a stone, there's no mathematical shape that you can ascribe to it. And if you want to find its volume, you have to use the method of immersion. Now you pour water inside a cylinder, a measuring cylinder, get the level of water, get the volume of water that was in that measuring cylinder. Now immerse your substance into it. We expect the level of water to rise. When it rises, the difference between the two levels of water should give you the volume that you have immersed, the volume of the object that you have immersed into it. Now, the extra liquid that you have, the liquid that rose because you have immersed your object, is what we call the liquid that you have displaced. The liquid that you have displaced. Of course, the space that liquid was occupying inside the body of the liquid has to leave that space because you are immersing another object inside it. So the liquid must now leave that space and go and settle somewhere else because there's no space for them anymore. It's more like you have a field class of students and a teacher walks in and he wants to sit in one of those seats. What he will ask he can ask one student to leave the class so that he can occupy that seat. Of course, that student will have no seat again if the class was originally filled. So the class students, let's now imagine that the students went out of the class. It means clearly that the student has been displaced because the teacher was trying to get a seat for himself within the class. That is exactly what is happening here. The liquid, we have a volume of liquid that has been displaced because we have an object that has been immersed into the liquid. So simply, the weight of this liquid that has been displaced, simply because you have an object inside it, is the upthrust that the liquid will exert on that object. So I will state the Archimedes principle again, and you see that. The Archimedes principle states that when an object is wholly means completely, totally, whole from whole number. When an object is wholly or partially immersed in a fluid, it will experience an upthrust, which is the weight of the liquid displaced by that object. So anytime an object is either wholly or partially immersed in a fluid, it must experience an upthrust. The object will experience an upthrust, and that upthrust is the weight of the liquid that you have displaced because the object has been immersed into it. So once we can find the weight, if you want to determine upthrust, once we can find the weight of the liquid that has been displaced, then that is the upthrust. I have a scheme that I always use for students to determine the upthrust that is experienced by an object that has been immersed inside the liquid. The very first thing is we must know the volume of the object. That's the first thing. What is the volume of the object? Of course, that can be given directly. If I have an object of 0.6 meter cube, that is its volume. What is the volume of the object? Sometimes that may not be given directly. I can give you the mass of the object. I can give you the density of the object, the mass and the density of the object. If I give you these two, then you should be able to find the volume. How? density is equal to mass all over volume. So the mass must be equal to, or the volume, sorry, must be equal to the mass divided by the density. So if the volume is equal to the mass divided by the density, then I can find the volume of the object. When I know the volume of the object, that's the very first thing. I will know the volume of the object that I have immersed. Where the object is totally immersed, it means the volume of the object is also the volume of the object that I have immersed. If, for example, an object has a volume of 0.6 meter cube, and I choose to immerse the whole of it inside a liquid, it means the volume of the object is 0.6. The volume of the object that I have immersed is also 0.6. But where the object is 0.6 and I immerse only half of it inside the liquid, it means the volume of the object is 0.6 and the volume of the object immersed is only half of the volume of the object, which is 0.6. 2 here 1, 2 here 0.3. So the volume of the object in that case that is immersed is 0.3. So there are instances where the volume of the object and the volume of the object immersed will be the same thing. That is if the object is totally immersed. It means the whole of it is what I have immersed. But there are also instances where the two of them will be different. It means the volume of the object is not going to be the volume of the object immersed. If I have the percentage of immersion, then I can use it to calculate the percentage or the fractional immersion. I can use it to calculate the volume of the object that is immersed. The volume of the object that is immersed must be the volume of the fluid that is displaced. The volume of the object that I have immersed must be the same thing as the volume of the object of the liquid I have displaced. Please look at it. Here I have immersed 5 centimeter cube of the object and it has displaced 5 centimeter cube of the object, of the liquid. How much of the object it goes into the fluid will help us to know how much of the fluid will be displaced. So always, anytime you know the volume of the object immersed, that is automatically going to be equal to the volume of the fluid that you have displaced. If you immerse 0.1, 0.1 of the fluid will be displaced. If you immerse 0.2, 0.2 of the liquid will be displaced. If you immerse 0.3, 0.3 of the liquid will also, or the fluid will be displaced. This particular equation is very, very important in the scheme towards finding the upthrust. Why? Because it helps us to cross from the object to the fluid. Before now, we're talking about the object. But from here now, once I know this and it becomes the volume of the fluid displaced, I can now continue. Now that I know the volume of the fluid that is displaced, I will know the density of the fluid. Once I know the density of the fluid and I join it to the volume of the fluid displaced, I can find the mass of the fluid displaced. Remember that the density is equal to mass all over volume. That means the mass is equal to density times volume. So if I use the density of the fluid multiplied by the volume of the fluid displaced, I must find the mass of the fluid displaced. That means if I know the volume of the fluid that is displaced, and I want to find the mass of this same volume, this same liquid, if I want to find the mass of anything, once you know the volume of that thing, just multiply it by the density. If I want to find the mass of any amount of substance, once I know the volume of that substance, I will just multiply it by the density of the substance. That will give me the mass of the substance. So if I know the density, the volume of the fluid displaced, I will multiply it by the density of the fluid and I will get the mass of the fluid displaced. So because I know the mass of the fluid displaced, I can multiply it by acceleration due to gravity and I will get the weight. The weight of a substance is the mass of that substance multiplied by acceleration due to gravity. That's one of the very important equations in physics. So if I want to find the weight of the fluid displaced, I will multiply the mass of the fluid displaced by the acceleration due to gravity, and that means if I multiply this by the acceleration due to gravity, I should get the weight of the fluid displaced. The weight of the fluid displaced is the upthrust that I need to look for. And that is the simple scheme for finding the upthrust on a substance anytime it is immersed inside a fluid. A very good example, if you want me to do a recap, know the volume of the object. That can be given directly or it can be given as the mass and the density of the substance, and you find the volume of the object. So once you know the volume of the object, know how much of it is immersed inside the fluid. When I know how much of it is immersed inside the fluid, I can find the volume of the fluid. Volume of the object immersed is the volume of the fluid displaced. If I know the volume of the fluid displaced, I'll multiply it by density. That gives me the mass of the fluid displaced. If I multiply it by the acceleration due to gravity, that gives me the volume of the fluid displaced. We'll take, as usual, we'll take one or two examples to further explain the concept. Now, we are told here we are asked to find, they said, what is the upthrust on a body which displaces 0.6 meter cube of water? What is the upthrust on a body which displaces 0.6 meter cube of water? That means that what I've been given is the volume. Volume of what? The volume of water that has been displaced. That substance upon immersion, of course, it is immersed in water. Upon immersion, we are not told if it is completely or partially immersed. So either of the two, it will experience an upthrust. So we are just told that that object displaces the amount of water displaced by that object is 0.6 meter cube. So this is a very simple question. They did not even want us to start from the beginning. They gave us the volume of the fluid displaced directly. So if I know the volume of the fluid displaced, the fluid is water. If I know the volume of the fluid displaced to be 0.6 meter cube, I can find the mass of the fluid displaced. That is water displaced. I told you how to find the mass of the fluid displaced. If you know the volume of the fluid displaced, it's simply going to be the volume of the fluid displaced. The fluid is water multiplied by the density of the fluid, which is water. The volume of the fluid displaced is 0.6 meter cube multiplied by the density of water is 1000 kg. If we multiply them, we should have 600 kilogram. If it is 600 kilogram, we can now find the weight of the water displaced. The weight of the water displaced must be mass of the water displaced multiplied by acceleration due to gravity. I gave you that earlier. So the mass of the water displaced is 600 kilogram multiplied by the acceleration due to gravity, which is taken to be 10 meters per second squared for this question, and it will be 6,000 Newton. Newton, because weight is a force and it is usually expressed in Newton. So that is the upthrust, and that is how to calculate the upthrust. There are more important applications of upthrust, particularly as regards equilibrium of an object in a fluid. If I just told you that anytime you place an object in a fluid, anytime you place an object in a fluid, that object will feel lighter to push out of the fluid. It will feel lighter to push out of the fluid. Why? Because generally, there are more than one force on that object. Number one, we have the weight of the object. The object itself, we have its weight. Usually that weight is referred to as its weight in air. The weight in air. If this object is 20 Newton, that 20 Newton becomes its weight. Normally, if the object is in air, if the object is 20 Newton, you will require a minimum force of 20 Newton to push it up, to take it up, to move it up. You will require a force of 20 Newton. If you apply a force that is less than 20 Newton, you will never get this body up. To get it up, you must require a force that is at least equal to the weight of the object. Now, the object's weight is not the only force that we have there. The fluid is helping you to exert an upthrust on that object. The fluid is helping you to exert an upthrust on that object. That means if there's a fluid around and it is exerting an upthrust of, let's say, 5 Newton, you don't need up to 20 anymore to push it up. Because ultimately, this object will not weigh as if it is 20 Newton. It will weigh as if it is 15. Why? Because of the 20, the liquid is helping you to push it up with 5. So to push it up, you only need 15. Yes, you need 20 to push it up, but the liquid is taking 5 out of that 20. So you only now need 15. So that means anytime an object is in a fluid, you need less than its weight to push it out. The force that you must exert to push it out, if it is a rope, that force is a tension. I can also call that force the apparent weight. I can call that force the apparent weight. So if you are asked to look for the apparent weight of a body in a fluid, it means what does his weight appears to be, apparent from the English word appear. What does his weight appears to be? His weight normally, if it is not in the fluid, is 20 in this case. So to push it up, I will need a force of 20. Now, with the upthrust, let's say there's an upthrust of 5. With the upthrust, it's not going to appear to weigh as if it is 20. The force liquid is already helping you to push it up with 5. So to now push it up, you only need to complement that 5 with 15. So 15 ultimately now becomes the apparent weight. That means while pushing it up, when it's still inside the liquid, the object appears to have a weight of 15 Newton. The moment it is out of the liquid, this 5 disappears. And once it disappears, you will now not be able to push it again with 15. You have to exert the full 20 Newton to be able to push it out. So most of the time, we can be asked to find the apparent weight that is required to just push the object or hold the object in the fluid. We can even be told that a balance is attached to it. Now, what will the balance measure? The balance will measure the force that is along the string that is connected to it from the object. If the string is carrying a force of 15 Newton, the balance will measure 15 Newton. Normally, if it is not inside the liquid, the balance, let us assume that it is 20, you will need a force of 20 to pull it out, so the balance will record 20. The balance always records the force that is acting along the string that is connected to the object. But where the object is inside a liquid, the balance will still record the force along that string, and I hope you know now that the force along the string will be slightly less than the weight because there's an upthrust. So generally what we just do is we will take an equilibrium of forces. We will assume that, okay, at the point you are trying to push it up or hold it up, the total forces upward must be equal to total forces downward. The total upward forces must be T plus U. T is upward because you are trying to pull it up or hold it up, and U, because the liquid is exerting an upward force on it, it must now be equal to the only downward force, which is the true weight of the object. The true weight of the object can either be given to you, or it can be given to you as the weight of the object in air. The weight of an object in air is the true weight of that object. Now, when we have a question, okay, before we move on, there are instances too where the upthrust will be more than the weight. In this type of situation, I'm assuming that the upthrust is less than the weight. That is why we need an additional upward force to complement the upthrust. There are instances where most of the time, when you drop an object inside a fluid, it goes down into the fluid. The reason why that is taking place is because the moment you drop an object inside the fluid, you are not holding it. When you drop an object inside the fluid, there are two forces on it, the weight of the object and the upthrust. There is no string that you are using to hold it. So when the object goes down, what the object is trying to tell you is that his weight is more than the upthrust. So it's having a net downward movement because there's a net downward force on it. If the upthrust of an object is greater than the weight, if the upthrust of an object is greater than the weight, the object will not sink. Instead, the object will float. That is what happens when you put objects like a football, a leather ball. If you try to immerse a leather ball into the water, the moment you remove your hand, the leather ball jumps up. Why? Because the upthrust on that ball is greater than the weight of the ball. So you expect that the object will be pushed back up. Now, in those instances where the upthrust is greater than the weight, the object will have its weight, the upthrust is upward. If I still want the object to stay down, if I want the object to stay down, then I must be ready to either press it down, because now it is the downward force that is less. The upward force is greater. So this object, without any assistance, will be pushed up. If I want it to stay down, then I must either use my hand to press it down. In that case, I'm exerting a downward force on it. I can now be asked to find what is the force that is required to hold it down. It is still equilibrium that I will take. In this case, the total downward force will be F plus W, while the upward force is what? U. I can now find that F by simply doing U minus W. There's another way by which I can hold the object down. I can tie it to the base of the container. I can tie it to the base of the container. There's a question like that I've seen before, that we're asked to find the force that is required to tie an object to the base, to the seabed. The seabed is the base of the seawater. So if you are going to tie it down, that means you are using a rope this time, and when you use a rope, there's a force that must be along that rope, and the name of that force is tension. It's the same with the one that is here too, but here you are holding it up, so the tension is up. Here you want to tie it down, so the tension is down. Tension is always along the rope, and it is always away from the object. So if that is the case, if this is the case, I can take equilibrium of forces. That becomes the total downward force, T plus W, must be equal to the upward force. The only upward force is U. So I can find T by also doing U minus W. We are going to try to see examples that can help us understand the fact that we have discussed thus far. Now, in the first question, we are going to take a body of mass 3 kg and volume 4 times 10 raised to power minus 4 meter cube. There's a body. The mass of that object is given to be 3 kg, 3 kilogram, and the volume of the object is given to be 4 times 10 raised to power minus 4 meter cube. We are told that it is hung from a balance graduated in Newton. This object is hung from a balance. This object is hung from a balance that is graduated in Newton. The balance is graduated in Newton. It's hung from a balance graduated in Newton. What is the reading on the balance? When it is 1/3 immersed in water. When it is 1/3 immersed in water. When 1/3 of it is immersed in water, what will be the reading on the balance? When it is 1/3 immersed in water. When only 1/3 of it is immersed in water, just a third of it is immersed in water, what will be the reading on this balance? What will be the reading on the balance? I think the first thing that we should do is to find all the forces, to indicate all the forces that will be on this object. It will have a weight that is sure. Because it is inside water or any fluid, it will have an upthrust. And because it is held up, it will have a tension. It will have a tension. I will now try to see if I can find each of those three. Of course, this balance will record the force that is acting between it and that is acting along the rope that is tied to the object. So if they are asking for what this balance will record, it is the tension. It is the tension. This balance will only record its weight if there is no other force. For example, when the object is in air, such that the only forces that we have there are the weight and the tension that is holding it up, then we expect T to be equal to W, because those are the only forces that are in the question. But here, T will not be equal to W because there's another force, upthrust, that is inside the question. So we now have to try to see how to go on with the question. The very first thing we should do is to find the weight of the object. I can find the weight of the object. The weight of the object is quite simply the mass of the object multiplied by acceleration due to gravity. Any weight is the mass multiplied by acceleration due to gravity. And luckily, we have been given the mass of the object 3. The acceleration due to gravity is 10. If we multiply them, we'll have 30 Newton. So the weight is 30 Newton. The tension I cannot find. I will have to see if I can find the upthrust. I want to see if I can find the upthrust. And the scheme for finding the upthrust is still on the board. I said you must know the volume of the object in mass, the volume of the fluid displaced, and the mass of the fluid displaced, the weight of the fluid displaced. That ultimately gives you the upthrust. So if I can continue with this, I'll check if I know the volume of the object. I don't know the volume of the object. Okay, I have the volume of the object to be 4 times 10 raised to power minus 4. If it is 4 times 10 raised to power minus 4, you can put it in ordinary form. This is 0.0004 meter cube. If I know the volume of the object now, I can find the volume of the object that is a mass. I like this question in the sense that it's going to allow us to use all of the quantities that I've written here. The volume of the object in mass, the whole of the object is having a volume of 0.0004. But it is not all of it that has been a mass. It's only this part, a third of it, given in the question, that has been a mass. So the volume of the object that has been a mass is just a third of the volume of the object itself. That is a third of 0.0004. And a third of 0.004 should give you 0.000133 meter cube. If that is the case, I can now say that I said once you know the volume of the object immersed, it automatically becomes the volume of the fluid that is displaced. So the volume of the fluid displaced must be 0.00133. I know the density of water to be 1,000. It has been given in the question 1,000 kg per meter cube. So once I know the volume of a substance, I can find the mass of that substance. I can find the mass of the water displaced by just simply multiplying the density by the volume. The density is 1,000. The volume is 0.000133. So when I multiply, I should have 0.133 kilogram. Now, I'm just a step away from determining the upthrust. The weight of the fluid displaced must now be mass of the water displaced multiplied by acceleration due to gravity. I said that here. When you know the mass of the fluid displaced, just multiply it by g, and that will give you the weight of the fluid displaced. If that is the case, that should be 0.133 multiplied by 10, and the answer should be 1.33 Newton. If the answer is 1.33 Newton, the weight of the water displaced must be the upthrust in water. So once I know the upthrust in water, I can now bring it straight into the question, and the upthrust is 1.33. I'll take the balance of forces. Upward forces must be equal to downward forces to be equal to get the tension, that will be the force which the spring balance will read. So total upward is T plus U. It must be equal to W, which is the only downward force that is there. T therefore becomes W minus U. Our W is 1.33. Our W is 30, sorry. And our 1.33, our U is 1.33 Newton. If we do that, we should have 28.67 Newton. And that is the tension, which will also be the force that this spring balance is going to record. Now we take one more example. We are told here that a fishing buoy is submerged in the sea by a cable anchored to the seabed as shown below. There's a seabed. This is a seabed. This is a buoy. There's a cable that is used to anchor it. This is the surface of the sea. This is the fishing buoy. So a fishing buoy is submerged in the sea by a cable anchored to the seabed as shown below. Now the buoy has a mass of 9.0 kilogram. The mass of the buoy is the object now, I can call it MB, is 9 kilogram, 9.0 kilogram. We are also given the volume of the buoy to be 0.12. the volume of the boy to be 0.12 meter cube. 0.12 meter cube. The density of the seawater is 1.1 times 10 raised power 3. The density of the seawater is 1.1 times 10 raised power 3 kilogram per meter cube. And we are told that we should draw and label in the diagram the forces acting on the buoy. What are the forces acting on the buoy? To know the forces that are acting on the buoy, all we just need to do is to review all that we have done. Remember that the buoy will have its weight. There will be an upthrust because it is inside the fluid. There will be an upthrust from the seawater on it. And ultimately, because it is tied to the seabed, there will be a tension along that rope that has been used to tie it. This can be achieved only in situations where the upthrust is definitely higher than the weight. When the upthrust is definitely higher than the weight, without this rope, we expect the upthrust, which is greater than the weight, to push out the buoy out of the seawater. But with the rope tied to the seabed, we expect that there will be a tension that will supplement or complement the weight in trying to equate it to the upthrust. So we can now continue to solve it. If we take the balance of forces here, we will see that total upward forces, that's T plus W, must be equal to the total upward forces, that is W, must be equal to total downward forces, that is T plus W. So we are looking for T. Okay, I've shown the forces. The question wants me to look for T, the tension. T clearly would therefore be W minus, or U minus W. U minus W. So I need to know the U and I need to know the W. How are we going to do that? Since I know the mass of the boy, getting his weight should not be a problem. When you know the mass of an object, the weight is known. You can find the weight. The weight of the boy will be mass of the boy multiplied by acceleration due to gravity. The mass of the boy in this case is 9, multiplied by the acceleration due to gravity is 10, and that becomes 90 Newton. So the weight of that boy is 90 Newton. I can find the upthrust. How will I get the upthrust? I'm going to use the same scheme that I've drawn out to get the upthrust. I will start from, do I know the volume of the object? Yes, I know the volume of the boy. So the volume of the boy is 0.12 meter cube. So I can find the next thing, the volume of the buoy immersed. What's the volume of the buoy immersed? It is 0.12 meter cube also. Why? From the diagram, we can clearly see that the buoy is completely immersed. If an object is completely immersed, it means the whole of its volume is immersed. So the volume of the object and the volume of the object immersed must be the same thing. So if I know the volume of the object immersed to still be the same thing, I can find the volume of the fluid that is displaced. The fluid in this case is the seawater. The volume of the seawater that will be displaced must be equal to the volume of the buoy immersed. These two are always equal. I said that here. The volume of the object immersed and the volume of the fluid displaced are always the same. So once I know the volume of the seawater that is displaced, I can find the mass of the seawater displaced. If I know the volume of anything, I can find the mass of that thing once I know the density. So I can easily say that the mass of the seawater displaced must the volume of the seawater displaced multiplied by the density of the seawater. So the mass of the seawater displaced must be equal to, what's the volume of the seawater? 0.12 multiplied by the density of the seawater. Density of the seawater is 1.1 times 10 raised power 3. So it means that the mass of the seawater displaced must be equal to 0.12 times 1.1 times 10 raised power 3. That will be 0.12 times 1.1 times 1 times 10 raised power 3. Here I have 132. 132 Newton is the mass of the seawater displaced. So the weight of the seawater displaced must be, according to that scheme, the mass of the seawater displaced multiplied by the acceleration due to gravity. And that will be 132 Newton, 132 kilogram. Sorry, the mass should be in kilogram. I beg your pardon. That's 132 kilogram minus 9, well, multiplied by 10. If we multiply that, we will have 1320 Newton. That will be the weight of the seawater displaced, which also translates into our upthrust. Now that we know the upthrust to be 1,320 Newton, then we can find the tension. How do we get the tension? The formula for the tension, based on what we got for the equilibrium of forces, the tension must be equal to the U minus W. The U in this case is 1,320 minus W is just 90. And if we subtract it, we are going to have 1,230 Newton. And that will be the tension along the cable that is used to hold down the buoy. Now, we will continue with our study of this principle by reviewing the law of flotation. The law of flotation is an extension of Archimedes' principle, and it's also a very important law that we have to review under density. The law of flotation states that an object will float in a fluid if its weight is equal to the upthrust of the fluid on it. An object will float in a fluid if its weight is equal to the upthrust of the fluid on it. That means, before now, all the questions that we have been solving are those questions that involves inequality between the weight of that object and the upthrust on the object, the weight of the object and the upthrust. I said earlier that if the weight is more than the upthrust, then we expect this object to sink and go down. So if you don't want that to happen, then you must be ready to hold it up with an additional force that will complement the upthrust. Alternatively, if the upthrust is more than the weight, if the upthrust is more than the weight, then we expect this object to jump back up when you immerse it inside the liquid. If you don't want that to happen, then you must assist the object by tying it down to the seabed if you don't want it to leave. But at any point, so in both cases that I've described, W is either greater or less than U. So, and the object will move in the direction of the greater force. But wherever W and U becomes equal, whenever W and U becomes equal, the object will just float. So anytime you see a floating object, it comes with the condition that at the point where the object is, the weight of that object has been completely balanced by the upthrust, and there is no other force that is on it. When an object is floating, anytime you see an object floating on the surface of water, it means it is at a level where the weight of the object, the weight of its weight is equal to the upthrust of the object. I can even by extension simplify that. It means if an object floats, anytime an object floats, the weight of the object must be equal to the upthrust. It means the weight of the object must be equal to the weight of the fluid displaced, because I had already said that the weight of the upthrust is the weight of the fluid displaced. Remember that we know that the weight is equal to the mass times acceleration due to gravity. That means anytime if I make mass the subject of the formula here, I'll get weight divided by acceleration due to gravity. It means if I multiply mass by acceleration due to gravity, I'll get the weight. Similarly, if I also divide weight by the acceleration due to gravity, I must get the mass. So if I decide to divide both by acceleration due to gravity, divide both sides by acceleration due to gravity, it means that weight of the object divided by acceleration due to gravity is the mass of the object. The weight of the fluid displaced divided by the acceleration due to gravity is the mass of the fluid displaced. So anytime an object is floating, we can use any of these relations. The actual one that is given to us by the law is the first one, but upon simplification, we are able to arrive at the third part, which says that the mass of the object will be equal to the mass of the free displaced. Mass of the object is normally not equal to the mass of the free displaced. This condition is only fulfilled anytime you are told in the question that the object is floating. When you are told in the question that the object is floating, it means this forms an additional equation that you can write for that problem. And we're going to try to review some questions to also explain the concept of law of flotation. We said again, don't forget that an object will float in a fluid if its weight is equal to the upthrust of the fluid, upthrust exerted by the fluid on it. An object will float in a fluid if its weight is equal to the upthrust exerted on the exerted by the fluid on it. Now let's see one or two questions that we can use to solve this problem. Remember again that the determination of upthrust does not change. We are still going to, if we need to calculate upthrust, we'll still use the scheme that is given to us by Archimedes' principle. We know the volume of the object, we know the volume of the object in mass, we know the volume of the fluid displaced, we know the mass of the fluid displaced, and we know the weight of the fluid displaced, which ultimately becomes the upthrust. The question we are going to solve under law of flotation is this. A cylindrical piece of wood of mass 200 grams and uniform cross-sectional area 40 centimeters squared, floats upright in water of density 1 grams per cm cube. It floats upright in water of density 1 grams per cm cube. The length of the wood immersed in water is dash. The length of the wood immersed in water is dash. Let me give you a graphic understanding of how the question looks like. We have water and we have a cylindrical wood, a piece of cylindrical wood floating on water. It is floating with a part of its body immersed. When object floats anyway, this is generally how we believe they float. A part will be in and a part must be out. It now depends on the density of the liquid and that of the substance to know, before we can know how much of it is in and how much of it is out. Now, we have this, we are given they said the mass of that wood is 200 grams. The mass of the wood is the object, the mass is 200 grams. It has uniform cross-sectional area of 40. It has a cross-sectional area that is uniform. The area is 40 centimeters squared. That's uniform cross-sectional area of 40 centimeters squared. It floats upright in water of density 1 grams per cm cube. The density of the liquid is water, the density of water is 1 grams per cm cube. We can continue. What is the length of the wood immersed in water? What is the length of the wood that is immersed in water? We want to find the length of the wood that is immersed in water, the length of the wood that is immersed. Let me call that length Li, the length immersed. It is not the whole of the length that they want us to find. This will be the whole of the length that they want us. It's not the whole of the length that they want us to find. Just the length, just the part of it that is immersed in water. To attempt this question, I want you to understand that when solid objects have uniform cross-sectional area, then it means that we can find their volume as area multiplied by height. When solid objects have uniform cross-sectional area, it means we can find their volume as area multiplied by height. Example of objects that have uniform cross-sectional area, we have a cylinder. A cylinder has uniform cross-sectional area. The width of the top, the width of the bottom, and the width at any other point along its cross-section are all the same. If that is not the case, then it does not have uniform cross-sectional area. A very good example of a solid object that does not have a uniform cross-sectional area in mathematics is a cone. We can see that the width of the top, the width of the middle, and the width of the bottom are all different. So this type of an object, I cannot find its volume from area times height. It's not possible. If a sphere too does not have a uniform cross-sectional area, so that is why it is not possible for you to find its volume from area times height. Cube has uniform cross-sectional area. Cuboid has uniform cross-sectional area. That is why when you check their volume, the calculation of their volume, the formula for calculating their volume, it follows the pattern area times height. A very good example. The volume of a cylinder is pi r squared h. That is because the volume is the area of the cross-section, which is a circle. The cross-section at any point is a circle. So it is the area multiplied by height. Just take the area of the cross-section and multiply it by height. The volume of a cuboid is also length times breadth times height. That is because it is area, because the cross-section, when you cut any part of a cuboid, it is a rectangle, and the area of a rectangle is length times breadth, then you are multiplying it by height. Anytime you have an object of uniform cross-section, once you know the area of the cross-section, just multiply it by the height. That should give you the volume of that substance. So we can continue from there. And there's another thing I must also tell you about this mathematical shape that have uniform cross-sectional area. Their volume, when you take any part of those solid shape, if I take any part of a cylinder, I hope you know that what I will have will still be a cylinder. Any part of it, what I will have will still be a cylinder. So the volume of that part will still be area times height. The only difference now is by cutting off some parts, I've reduced the area. I've reduced the height. I've not reduced the area. The area is not possible for me to reduce the area, but I can reduce the height by cutting off a part of a cylinder. What I will have will still be a cylinder, and I can use the formula area times height. Now, I want us to come back to the question and try to see what we have. The very first thing, and that will guide our solution, is the knowledge of the fact that within the question we are made to understand that this object is floating. When an object floats, anytime an object floats, it means that the volume of the object, the mass of the object, must be equal to the mass of the fluid displaced. I said it before. From the law of flotation, an object will float when its weight is equal to its upthrust. Its upthrust is the weight of the fluid displaced. And if we divide both sides by g like I did the last time while I was explaining the law, it means the mass of the object must also be equal to the mass of the fluid displaced. So I can bring in what I have here and just put it there. Mind you, the fluid is water. Because it is floating, that is why I'm able to get this expression, and I can work with that expression. The mass of the object, luckily, is given to me as 200 grams, and because it is floating, that will also be the mass of the water displaced. Don't forget. So from that relationship, I've been able to get the mass of the water displaced. So the mass of the water displaced is 200 grams. Because I know the mass of the water displaced, and I know the density of water, 1 grams per cm cube. I know the density of water. I can find the volume of water displaced. I can find the volume of water displaced. When you know the mass, you only need to know the density to be able to calculate the volume. When you know the volume also, you only need the density to calculate the mass. With density, you can convert mass to volume. With density, you can convert volume to mass. Now, the volume of the substance must be mass of the water displaced divided by the density of water. What is the mass of water displaced? 200 grams divided by what's the density of water? The density of water is 1. So the volume of the water displaced must be 200 cm cube. Note that I am working in grams and cm cube here because that's the predominant unit in the question. Now I can continue. If I know the volume of water displaced, that will also be equal to the volume of the object immersed. What I am doing is just the same with taking this equation, this scheme, now working backward. I was used to working from volume of the object down to getting upthrust. In this case, I know the mass of the fluid displaced. So I've been able to use that one to get the volume of the fluid displaced. And now that I know the volume of the fluid displaced, it is the volume of the object that is immersed. And now, please, I know the volume of the object that is immersed, just the part of this object that is immersed. I know it. I know the part of this object that is immersed. And once that is done, I can find what I need to find, which is the height or the length that is immersed. Mind you, I said that any part of a cylinder is also a cylinder. So if you want me to find the volume of this object, the wood that is immersed, because it is still a shape of constant cross-section, I can use this to find its volume. The area is 40 centimeters squared. Area times the length immersed or the height immersed. The area is 40 centimeters. The height immersed is just Li, and that is equal to the volume of the object immersed that I already have as 200 cm3. So the length immersed must be equal to 200 all over 40, and the answer is 5 centimeters. You might be worried about the fact that why did I not use the whole of the length? Why did I use only a part of the length? Because that is what is immersed. It is the volume that is immersed that I've been able to get. So it is the volume that is immersed that I actually need. I don't need the whole of the volume of that cylinder. Yes, I understand that in floating, some part of the cylinder, we have them up, while some part is down. It's the one that is down that is immersed that the question wants me to find, and that is what I've been able to get for you. So we'll continue from there. Now we are going to review relative density, and that's the last part of density that we have to move to. Relative density, I give you the simple formula for relative density. I said the relative density of a substance is the density of that substance all over the density of water. It does not have units because you are dividing two quantities that have the same unit, so you expect the units to cancel out. But why are we coming back to it? It is because relative density has some other formulas that we can use to calculate it. In fact, there is no other quantity in physics that has the number of formulas that you can use to represent relative density. It all depends on how much of it you know. So now we are going to try to see how we can get all some other formulas from this particular simple equation that we can use to find relative density. Now, we all know that the density of a substance is the mass of the substance divided by the volume of the substance. So if I decide to put that one into this equation, I will say that the relative density of a substance is, instead of writing the density of that substance, I will write it as a mass of the substance all over the volume of the substance. Then I will divide by, instead of writing the density of water, I will write the mass of water all over the volume of water. If we do that by simplification, we should have mass of the substance all over volume of the substance. Subscript S is representing the substance, while subscript W is representing water, divided by the mass of the water all over the volume of water. So the relative density of that substance therefore becomes mass of the substance all over volume of the substance multiplied by, if I change this to multiplication, it becomes volume of water all over mass of water. If it is now possible for us to find if it is possible for us to make the volume of the substance and the volume of water to be equal, if it is possible for us to make the volume of the substance and the volume of water equal, if that is possible, then we can easily say that this can cancel out this. Because they are equal, we can now say that the relative density of the substance can be mass of the substance all over mass of equal volume of water. This formula also shows that we can use masses to find or calculate the relative density, provided their volume are equal. And it is so easy for me to get equal volumes of two different substances. For example, if I have a cup, or I have two similar cups, 2 cups of the same volume, or 2 gallons of the same volume, if I fill one with the substance and I fill the other with water, I can use the mass of the substance and the mass of this water to calculate the relative density of the substance. How would that be? I told you that if it is possible for you to get equal volume of a substance and water, then you can use mass. Instead of using density to calculate their relative density, you can use their masses to get the relative density. In doing this, all I need to do is I must have measured the mass of the empty can. Let's assume that the mass of the empty can is 20 grams. Now, when it is filled with water, with the substance, when it is filled with the substance, let us assume that its mass when filled with the substance is 45 grams, and its mass when filled with water, that same cup when filled with water, is 50 grams. It clearly shows that the mass of the substance will be 25 grams. How did I get 25 grams? This 45 represents the can and the substance. And since the can alone is 20, I can just subtract 20 from 45 to get 25. The same thing for water can be done. The mass of the water that will fill that same can will be 50 minus 20, because this 50 represents the can and the water that is filling it. So the mass of the water alone is 30 grams. So we can find the relative density of the substance. How can we get the relative density of the substance? It will be the mass of the substance divided by the mass of equal volume of water. And since I've used similar can or the same can, I'm so sure that they have the same volume. So I can use mass to calculate their relative density. That becomes 25 all over 30. Now divide that to get the answer. What I'm saying in essence is, if it is possible for you, if I've asked you to find the relative density of a substance, check if you know the density of the substance and that of water divided. But if you don't know this directly, you can also use mass, their mass values, to get the relative density. How can that give you the relative density? That can give you the relative density if you are able to get the substance for which the relative density is required and water, you are able to get equal volume of the two. Then you can find the mass of the substance, find the mass of water, then divide them to get relative density. Note that mass cannot be used to find relative density. It can only be used to find relative density on the condition that the volume are the same. And there are so many other applications under density where we can get equal volume of a substance and water. Let us assume that we have water inside a can, and the substance is completely immersed in that water. The substance is completely immersed in the water. Quite simply, I can get the mass, or before we even move into that, I can also continue with this relationship. If now we know that the relative density of a substance is mass of the substance over mass of equal volume of water, if we multiply both the numerator and denominator by acceleration due to gravity, after already establishing that the weight is mass times acceleration due to gravity, we can now say that the relative density of a substance is the mass of the substance times acceleration due to gravity is the weight of the substance. The mass of equal volume of water times acceleration due to gravity will be weight of equal volume of water. So this also gives us an additional equation that we can also use to find the relative density of the substance. So now we have three. We can use the ratio of their densities, that's if the density values are known. We can use the ratio of their masses, that is if it is possible for us to have equal volume of the two. We can now also use the ratio of their weights to find the relative density, provided also that the volume are the same. The volume of the substance and the volume of water are both the same. So we can now expand on this. If we have water in a can and we immerse an object completely into it, we know that that object we have is weight. Let us call his weight W0. That's the weight of the object. Now we know that that object, now that it is in water and is completely immersed, it will be exerted upon by the upthrust from the water. The water will exert an upthrust on the object. Now, we know the meaning of this upthrust. Upthrust means the weight of the water displaced by this object. And I told you that since the object is completely immersed in water, the water that will be displaced will have the same volume with the object. I said it before, that the volume of the object that is immersed must be the volume of the fluid or the water that is displaced. If an object is completely immersed, the volume that that object will have will be the volume of the fluid that is displaced. Will be the volume of the fluid that is displaced. That means that the fluid displaced and the object that is immersed must have the same volume if it is completely immersed. So now, it means if I know the weight of this fluid displaced, if I know the weight of this fluid displaced, and I know the weight of this object, I can find the relative density of the object. Since relative density of a substance can be found by dividing the weight of the substance and the weight of water that has the same volume with it. Now that I've established that this object and the water displaced, not the whole of the water that is displaced and the object have the same volume, I can use the two to determine the relative density of that object. So I can now say that the relative density of an object is the weight of the object expanding on this formula all over the weight of equal volume of water. Now, this water that has equal volume with it, its weight will be called the weight of the water displaced. And the weight of the water displaced by that same object is the upthrust, because Archimedes said that the upthrust is the weight of the fluid displaced by the object that is placed into it. So the weight of the water displaced is the upthrust of water on the object. So I can now continue with this by saying that the weight of the object all over the weight of the equal volume of water can also be referred to as the upthrust of water on the object. So clearly, I can find the relative density of an object if I know the weight of the object and I know the upthrust that water is exerting on the object. It must specifically be water, because the denominator has to do with water anytime we are using the formula of relative density. Now, we can do more than that. What if I want to find the relative density of a liquid? If I want to find the relative density of a liquid, I can get the liquid inside the container, and I can also get water inside the container. This is the liquid. Let's call the liquid X, and this is water. Now, I can put an object inside the liquid. We expect some amount of the liquid to be displaced if the object is either partially immersed or totally immersed. I can also remove that object and put that same object in water. I expect some amount of water to also be displaced if it is either partially or completely. But what we need here to do is the object will have to be completely immersed. Now we understand that this segment of the liquid will be called the liquid displaced. This segment of water, as I said in this last illustration, will be called the water displaced. Now, the two of them must have the same volume. Their volume must be the same. Why? The volume of a liquid displaced must be equal to the volume of the object immersed. And since I'm using the same object, if this object is 2 centimeter cube, this one is also 2 centimeter cube, the volume of the object that I have immersed must be the volume of the fluid that is displaced, and the volume of the fluid that is displaced. So if 2 centimeter cube object is immersed into a liquid, 2 centimeter cube of the liquid will be displaced. If 2 centimeter cube of an object is immersed into a fluid, then into water, then 2 centimeter cube of water will be displaced. It means the water displaced and the liquid displaced must have the same volume. When they have the same volume, I can use my formula. Once I get the same volume, I can use weight or mass to find the relative density. The question can now be set that I should find the relative density of that liquid X. The relative density of the liquid X can be said to be the upthrust of X on an object all over the upthrust of water on the same object, because it is only when it is the same object that we will be talking about the same volume. So that is also another formula that can also be used. And there is even more formula that we can use to get relative density. I will take 1 or 2 examples on this, and we will continue from there. We are told that an object weighs 30 Newton in air and 21 Newton in water. The weight of the object when completely immersed in the liquid
of relative density 1.4 is dash. An object weighs 30 Newton in air, 21 Newton in water. What is the weight of the object when completely immersed in a liquid of density, relative density 1.4? So easy. We can decide to solve that. The weight of the object in air is 30 Newton. The weight of the object in water is 21. When we are given the weight of an object in a liquid, it is the apparent weight, the weight that it will feel like it's having when it is inside that liquid. The weight that it will feel like it's having when it's inside the liquid, that's the weight of the object in a liquid. It's different from its actual weight. This is its actual weight, it's still 30. But if I need to pull it out, I just need to pull it out with 21. Why? Because there's an upthrust. And we can easily get the upthrust here. The upthrust is equal to 9. We just need to subtract 30 from 21 by taking the balance of forces. Total upward forces must be equal to total downward forces. So upthrust of water on that object will be 9. Now, this is water. The object is now placed in a liquid whose relative density is 1.4. What will be his weight? The apparent weight inside that liquid. Mind you, his weight will still be 30, but we don't know his upthrust in that liquid. We don't know the upthrust in that liquid if it is the same object. So we can easily use the formula that I just gave you to determine the upthrust in the liquid. When you know the upthrust in the liquid, then you can now find the weight of the object in that liquid. Now, I can say that the relative density of the liquid is the upthrust of the object, upthrust of the liquid on the object all over the upthrust of water on the same object. I know the relative density I've been given in the question is 1.4. The upthrust of the liquid on the object I don't know, but the upthrust of water on the same object is 9. I've just calculated it. The upthrust of the liquid on the object will now be equal to 1.4 times 9, and 1.4 times 9 should be 12.6 Newton. If it is 12.6, I can now find the weight that the object, the apparent weight of the object, the weight that the object will have in that liquid. How will I get the weight that the object will have in that liquid? It will clearly be equal to, if I take the balance of forces, upthrust plus the apparent weight, because they are both upward, must be equal to the weight of the object. So the apparent weight must now be equal to the weight of the object minus the upthrust. The weight of the object must be 30. The upthrust is 12.6. It means the object will weigh 17.4 Newton in that liquid. And that is what we are going to have as the answer. It's even possible that we express relative density in terms of volume. Mind you, we said relative density, the formula for finding relative density of a substance is the density of that substance all over the density of water. So that means the relative density of the substance must be equal to, if we have to split these two, mass of the substance all over the volume of the substance divided by the mass of water all over the volume of water. So if that is the case, we can continue with the simplification. Relative density of the substance must be mass of the substance over volume of the substance times the volume of water all over the mass of water. So if that is also the case, then we can now say that the last time we assumed that their volumes are equal. Now let us assume that their masses are the same. Let us assume that their masses are the same. If their masses are the same, what do we have? If their masses are the same, we can say that the mass of if the mass of the substance is equal to the mass of water, then we can say that the relative density of the substance must be equal to the mass of the substance. Let's just call it M, all over the volume of the substance times the volume of water all over the mass of water, which is the same. Now, if we cancel out the two masses because we assume that they will have the same mass, we will say that the relative density of the substance must be equal to the volume of water all over volume of equal mass of the substance. Of course, it is a little bit more challenging to get equal masses of two different, particularly liquid, but we can still get it in special application, particularly applications that involve flotation. When an object floats, let us assume that an object is put in a liquid L and is also put in water. If it will float in either of the two, if it will float in the liquid and it will also float in water, it will not float by equal amount of its volume in both. It is possible that, let us assume it is a cylindrical object, in one, more of it will be immersed than in the other. In one, more of it will be immersed than in the other. But one thing we know is that as long as it is floating, we expect that is the equation of flotation will be true. And what's the equation of flotation? The weight of the object must be equal to the upthrust. And the upthrust, I said, is the weight of the fluid that is displaced. And I also said that we can divide both by acceleration due to gravity. That was said at the start of this class. So the mass of the object and the mass of the fluid displaced must be the same. Here too, the mass of the object and the mass of the fluid displaced must be the same. This is water displaced by the object. This is the liquid displaced by the object. So if we are using the same object, their masses are the same. It means at this point of flotation, the mass of the liquid displaced and the mass of the water displaced must also be the same. And if the masses are the same, it means that we can actually continue with the simplification. And it is a very good example of where we can get equal masses. We can actually continue with the simplification, and we can say that the relative density of a liquid can, now that we have their masses being equal, we can now use the proportion of the volume that is a mass to determine there's a volume that will be displaced here. There's a volume of the liquid that will be displaced. There's also a volume of the liquid that will be displaced here. The two volumes will not be the same thing. It is not possible that the two volumes are the same because you have the extent of immersion of the object that led to flotation in the two is not the same. It is more immersed here than in this. So we'll say that since the masses are the same, we can say that the volume of the object immersed in water must be all over the volume of the object immersed in the liquid. L will give us the relative density of the liquid. So we can use the extent of immersion of an object when floating to determine the relative density of that liquid according to this formula. And that should be where, and a very good example that we can use to solve this is, we are told that a piece of wood of uniform cross-sectional area floats upright in a liquid of relative density 0.8. Is floating upright in a liquid of relative density 0.8. The question now is, with 1/3 of his height above the liquid. 1/3 of his height is above the liquid. 1/3 of his height is above the liquid. That means 2/3. If we just, because once a particular dimension is expressed in fraction, we can find the other side by just subtracting it from 1. So if 1/3 is above the liquid, 2/3 will be inside the liquid. So it's 1/6 of his height. 1/6 of his height is above the liquid. Here, 5/6 will be below the liquid. Now, If placed in water, what is the fraction of its height above the water level? What will be the fraction of its height that is above the water level? We can determine the fraction that is below the water level first. Then we'll find the fraction that is above the water level. And that is what we just need to do. So I will dictate the question so that we have it. A piece of wood of uniform cylindrical section floats upright in a liquid of relative density 0.8 with 1/6 of its height above the liquid. If placed in water, what fraction of its height will be above the water level? What fraction of its height will be above? Of course, before you can use volume to find relative density, express relative density, it must be in a flotation question. If it is not in a flotation question, don't use volume to find it, because it's only when the object is floating in both water and the liquid that the condition that is required for us to use this equation will be set. Now, we can say that the volume, I can take that, remember that the volume of an object that has constant cross-section is area times height. So I can say that I can convert those, I can express those heights in terms of this fraction. If the height of this object is h, it means the height that is above the water will be 1/6h, and the one that is beneath the water surface is 5/6h. I don't know the fraction that is beneath the water surface. Let me just call it x. So it will be xh, where x represents a fraction. The remaining part will be 1 minus x. The height is still h. So now I can say that the relative density of the liquid, which is given, is 0.8, is the volume of the object immersed in water. How do we find the volume? We assume that the cross-sectional area is A. Since it is the same cylinder, we assume that the cross-sectional area is A. So the volume must be equal to area multiplied by height. What is the area in this case? I think the area is A multiplied by the height. The height in water will be x times h all over the volume of the object immersed in the oil. The volume of the object immersed in the oil will be area multiplied by 5/6, that's the height, h. And I can complete this. A cancel out A, h cancel out h. So I can say that 0.8 is equal to x all over 5/6. I can cross multiply. My x should be equal to 0.8 multiplied by 5/6. My 0.8, if I take it to fraction, should be 4/5 multiplied by 5/6. 5 obviously cancel out 5. 2 here 2, 2 here 3. It means that the fraction that is beneath the water surface is 2/3. If the fraction beneath the water surface is 2/3, then the fraction that is above the water surface will be 1/3, clearly. And that is what they want us to determine. So the answer should be 1/3, or more appropriately 0.33 if you want to express it in decimal. So clearly I can even extend this formula by saying that the relative density of a liquid is the height of an object floating in water all over the height of the same object that is floating in the liquid. Because that simply would have just been able to give us the answer. But one other thing I want you to do before expressing this is the object must have constant cross-sectional area. That's why the area is cancelling out. If the object does not have constant cross-sectional area or fixed cross-sectional area, then you can just use volume and can just leave it like this. Now we move on to the last part of the topic, and that is the instrument that is used to measure relative density. The instrument that is used to measure relative density is an hydrometer, D for density. There is an hygrometer that we are still going to see later. That does not have anything to do with density. An hydrometer is used to measure relative density. Hydrometer is used to measure relative density. It is one of the simplest things to draw in physics. It has a narrow stem, it has a wide bulb, and it has a loaded bottom for lead shot. It has a stem, a narrow stem, it has a bulb, and it has lead shot at the bottom. An hydrometer measures the relative density of a liquid by immersion. We have to just immerse it inside the liquid. It will float inside the liquid, and it will float with a part of it directly above the liquid surface and a part of it immersed in the liquid surface. The level of immersion will give us the relative density of the liquid that we are trying to measure. So the lead shot will ensure that this hydrometer stays upright in the liquid that we are trying to use it to measure the relative density of. The bulb ensures that the hydrometer is completely immersed, while the narrow stem ensures the sensitivity of the hydrometer. It assures that the hydrometer, when you put it inside the liquid, is able to measure the relative density and dictate slight change in density of that substance. So that is an hydrometer. With that, I think we have come to the end of this topic. Thank you very much. Join us the next time for another interesting treatment of another topic in physics.